Safety Lesson 1 covers the principles of radiation physics, the foundation of everything else in the safety category, which makes up 25% of the ARRT registry exam. Understanding how X-rays are produced, how they interact with matter, and how they behave in tissue is non-negotiable knowledge. 12 minutes. Let's build the foundation. 5 steps produce every diagnostic X-ray. Thermionic emission. The cathode filament is heated by an electric current. When hot enough, electrons are boiled off the tungsten filament surface. This is the electron cloud. Electron acceleration. The high voltage applied across the tube, the kilovoltage peak, or kVp, accelerates electrons from cathode to anode at very high speed. Focusing. The focusing cup directs the electron stream toward the focal spot on the anode. Target interaction. Electrons strike the tungsten anode target. About 99% of kinetic energy becomes heat. About 1% becomes X-rays. And X-ray emission. X-rays exit through the tube window, through filtration, and form the useful beam. 2 types of X-ray production at the anode. Bremsstrahlung radiation, which means breaking radiation in German. An incoming electron passes near a tungsten nucleus, slows down, and loses energy. That energy is released as an X-ray photon. The photon's energy depends on how close the electron passes. This produces a continuous, broad spectrum of energies. Bremsstrahlung makes up approximately 80 to 90% of the diagnostic X-ray beam. Characteristic radiation is different. An incoming electron ejects an inner shell electron from the tungsten atom. An outer shell electron drops down to fill the vacancy and releases energy as an X-ray with a specific, discrete energy, the characteristic energy of that shell transition. This produces only at certain energy levels and only occurs when kVp exceeds 70 kilovolts for tungsten. 4 technical factors control the X-ray beam, and each one controls a specific beam property. kVp, kilovoltage peak, controls beam quality, which means penetrating power. Higher kVp produces more energetic photons that penetrate tissue more easily. It is the primary controller of subject contrast and patient dose efficiency. MAS, milliampere seconds, controls beam quantity, the number of photons produced. MAS directly determines patient dose and image density. Double the MAS, double the dose. SID, source to image distance, affects intensity. By the inverse square law, doubling the SID reduces intensity to 1/4. Standard table, 40 inches. Standard chest, 72 inches. And focal spot, the area on the anode where electrons strike. Small focal spot for detail. Large focal spot for high output work. 4 interactions matter for diagnostic radiography. Coherent scattering, no energy transfer, no ionization, direction changes only. Negligible in diagnostic range. Photoelectric effect. A photon is completely absorbed by an inner shell electron. The electron is ejected. This produces characteristic radiation and contributes strongly to image contrast. Dominant at lower kVp. Higher patient dose than Compton at the same photon energy. Compton scattering. A photon interacts with an outer shell electron, transfers some energy, and scatters in a new direction. The scattered photon carries energy and becomes a source of occupational exposure and image fog. Dominant in diagnostic imaging. Primary cause of scatter to the radiographer. And pair production only occurs above 1.02 million electron volts. Not relevant in diagnostic radiography. You'll see it on the exam. Just know it doesn't apply to your clinical work. The inverse square law is one of the most important and most tested physics principles in radiography. The intensity of radiation is inversely proportional to the square of the distance from the source. Written as a formula, I1 over I2 equals D2 squared over D1 squared. In practical terms, double the distance from the source and the intensity drops to 1/4. Triple the distance and intensity drops to 1/9. This is why distance is the single, most practical radiation protection tool available to the radiographer. Every foot of additional distance during a portable exposure meaningfully reduces your occupational dose. Use the full length of your exposure cord. Every time. X-rays are part of the electromagnetic spectrum, a range of energy forms that all travel at the speed of light. In order from lowest energy to highest: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. X-rays and gamma rays are both ionizing radiation. They carry enough energy to remove electrons from atoms. This is what makes them medically useful and potentially harmful. The key distinction between X-rays and gamma rays is their origin. X-rays come from the electron cloud around the nucleus. Gamma rays originate from inside the nucleus itself. Clinically, both are ionizing, and both require the same protection principles. 8 properties of X-rays that the Registry tests regularly. X-rays travel in straight lines. They cannot be bent. They travel at the speed of light. They are invisible. You cannot see, smell, hear, or feel them. They cause ionization, removing electrons from atoms they interact with. They affect photographic film and digital receptors alike. They cause biological effects at the cellular level. They are attenuated, meaning absorbed, by matter in proportion to tissue density. And their dose is cumulative. There is no safe threshold below which no biological effect occurs. Under the linear non-threshold model, or LNT model, 1% of the electron kinetic energy at the anode becomes X-rays. 99% becomes heat. Managing heat is one of the primary engineering challenges in X-ray tube design. Heat units measure the thermal load placed on the anode. Heat unit formula, HU, equals kVp times MA times seconds times a generator factor. The rotating anode distributes heat across a larger surface area by spinning. Standard rotation, 3,300 to 3,600 revolutions per minute. High speed, 10,000 revolutions per minute. Anode cooling charts must be consulted before high-demand procedures, fluoroscopy, rapid serial exposures. Exceeding the heat load capacity damages the tube and ends the exam. Tube cooling time is real and must be respected. 3 radiation physics questions. Think before the answer drops. The answer is C, Compton scattering. Compton interaction is the dominant interaction in the diagnostic energy range. The scattered photon retains significant energy and travels in a new direction, reaching the image receptor as noise and the radiographer as occupational dose. This is why collimation and shielding are so critical. The answer is C. The intensity is reduced to 1/4. By the inverse square law, doubling the distance reduces intensity by the square of the distance ratio. 2 squared equals 4. Intensity at the new position is 1/4, 1/4 of the original. Double the distance, quarter the intensity. The answer is C. It accounts for approximately 80 to 90% of the diagnostic X-ray beam. Bremsstrahlung radiation results when electrons decelerate near the atomic nucleus, producing a continuous spectrum of X-ray energies. It makes up the vast majority of the diagnostic beam. You just covered X-ray production, Bremsstrahlung and characteristic radiation, beam characteristics, photon interactions, the inverse square law, the electromagnetic spectrum, X-ray properties, and heat management. This is the physics foundation everything else builds on. Keep drilling in the practice section.